So let's talk about a huge problem in AI right now. These models are getting unbelievably powerful, but they're also getting, well, just unbelievably huge. They're expensive and they eat up a ton of resources. Which brings us to the big question we're tackling today. Can we actually get more from less? So, yeah, here it is, AI's big problem. This isn't just a minor issue, it's a real growth dilemma. As these models just keep getting bigger and bigger, they're creating this massive challenge that the whole industry is starting to bump up against. And look, this isn't just some techie problem for engineers to solve. It's a real barrier to innovation. When a model is this gigantic, only the biggest companies with the deepest pockets can really afford to build and run them. And that locks out smaller companies, indie developers, and researchers. It basically slams the door on the very creativity we need to push this field forward. But what if there's another way to do this? And that's where something like the new, leaner Gemma 4 comes into the picture. It's a powerful model that could really change the game. But the real question is, can you actually shrink a model down without making it, dumber? I mean, just look at these numbers. The difference is pretty dramatic, right? The original Gemma 4 is this heavyweight, coming in at about 52 gigabytes. But the pruned version, it's down to a much more manageable 43 gigs. That's an 18% drop in size. So how in the world do they pull this off without losing all that brain power? Well, the secret sauce, if you will, is this really clever technique called expert pruning. And this isn't just about randomly hacking away parts of the model. No. It's way more like a surgical procedure designed to trim away the unnecessary fat while keeping all of the muscle. Okay, so to get how this works, you first got to understand the model's design. Gemma 4 uses what's called a mixture of experts, or MOE. The best way to think about it is like this. Imagine you've got this huge team of specialists on call. For Gemma 4, we're talking 128 of these experts in every layer. But here's the really smart part. For any one job, it only calls up 8 of them, the absolute best ones for that specific task. And that leads to a really brilliant question, right? If you've got 128 specialists on the payroll, but you're only ever using 8 at a time, are all of them really pulling their weight? What if some of them are just kind of sitting on the bench all the time? Or what if their skills overlap a little too much with other experts on the team? And that's exactly where this method called REAP comes into play. You can think of it like a 2-step efficiency check. First up is calibration. They take the model and run it through this huge data set. We're talking 22,000 different examples of coding, math, reasoning, you name it. And all they're doing is watching. Which experts get called up the most? Which ones do the best job? Then comes step 2, pruning. With all that data, the algorithm goes in and smartly identifies the bottom 20%, the least valuable players, essentially, and removes them. That's 25 out of 128 experts in each layer that get the boot, leaving behind a much leaner, more focused team. Okay, so that's the theory, right? A smaller, more streamlined team should be more efficient. But the billion-dollar question is, does it actually work? Can this leaner model really go toe-to-toe with the original? Let's actually look at the numbers and see what happened. All right, and the results, honestly, they're pretty fascinating. On really tough stuff like elementary math and that GSM-AK benchmark, the performance is almost the same, just a tiny dip, barely noticeable. But then, and this is the wild part, look at college computer science. The pruned model doesn't just do okay, it blows the original out of the water by 20 points. This kind of suggests that by getting rid of those redundant, maybe noisy experts, the model actually got more focused. It's a perfect example of how sometimes less really is more. Okay, numbers are one thing, but what does it feel like to use? When actual humans put the two models side by side and compared what they generated, they found something really powerful. On generation quality, the two were pretty much indistinguishable. The smaller model is just as creative, just as coherent, and just as useful. So let's just break this down. You take out a full 20% of the experts. A fifth of its specialized workforce is gone. And in return for that cut, you keep about 98% of the performance on those really key tasks. That is an absolutely incredible trade-off. A huge, huge win for efficiency. Okay, let's zoom out for a second because this is about way more than just one model. What we're seeing here really points toward a much more sustainable and, frankly, a much more accessible future for all of AI.
So why should you care about all this? Well, a smaller AI means it can run on hardware that's way less expensive, stuff you might actually have, not just what's in a giant data center. That brings the running costs way down, both in terms of money and energy. But the most important thing, it puts these amazing tools back into the hands of more people, more developers, more researchers, more creators. And that's what's going to speed up innovation for all of us. It's a path forward that's about being smarter, not just bigger.
And that kind of leaves us with one last thing to think about. For the longest time, the race in AI has been all about scale, about who can build the most massive model. But maybe this is a sign of things to come. Maybe, just maybe, the real future of AI isn't about who can build the biggest thing, but who can build the smartest thing.